Hello, and this is video number 2 for week 5 of assembly language csc314. And this is going to be a really short one because I realized I didn't point something out in the last video early on, and I just want to make sure that you see it. Just to clarify, and it had to do with the example instructions here. These two instructions here, where we're moving a 4-byte or double word into EAX, and then we're moving a 2-byte word into AX. And remember that AX is just the lower half of EAX. And we talked about that quite a bit, but what we did not do is look at what was actually going to happen in the register. At least I'm pretty sure I didn't point this out directly. So let's come over here to KDGB and let's set a breakpoint right there. Let's run to finish out, because this is just leaving off where I was in the last video, and then I'm restarting, running up to that point. So right now we're about to move this hexadecimal 1, 2, 3, 4, 5, 6, 7, 8 into register EAX. So again, that comes from, if we look at where these instructions are in memory, here's the instruction we are on. So we're about to do that. And of course, if we look at this as bytes, and let's see, that's 80AA. Whoops, I have to do hexadecimal bytes. There we go. So 80AA, that's somewhere in here. There it is. There's the 1, 2, again, little endian, so backwards 1, 2, 3, 4, 5, 6, 7, 8. And then here is the opcode for that. The B8 is the opcode to copy that 32-byte number or 32-bit number into EAX. So starting on the byte that my mouse is on right now, that is the instruction we're about to do in machine language. And so that's going to copy these 4 bytes, little endian style, into register EAX. So let's go ahead and now let's do the step, and sure enough, we see in register EAX, we see those bytes. Now, the thing that I did not focus on, I discussed it, but didn't really focus on it to illustrate it. Now we're going to move a 2-byte word, a regular word, not a double word, into AX. AX is just the last 4 hexadecimal digits here. That's the last 16 binary digits of that register. So if we go and look at this as binary, and you count 16 from the end here, I wish it would have spaces or something to break these up a little bit, but we can see, I think right about there, that's 16 bits where my mouse is. Not sure I have quite on the right breakpoint. Let's see, 1, 2, 3. 8, 7, 6, 5. There. Now my mouse is on the breakpoint between 16 bits. So everything to the right of where my mouse is pointing, those bits are going to be affected by this move operation, copying these 16 bits into register AX, which is just the second half of EAX. So let's do the step over and see that. Boom. So remember, F is 4 1-bits, so this is 1111 1111 0000 0000 in binary, and you'll see that right there at that break between the two halves, we see that we got 8 1s followed by 8 zeros, which is exactly what should have happened as a result of doing this instruction. So hopefully that makes clear that if you change AX, you are also changing the lower half of EAX, but the upper bits of EAX were unaffected. So sometimes if you only need to work with smaller integers, 16-bit integers, you can kind of shuffle things around. You can copy things, because there's ways to shift bits around in the registers that we'll be learning on later on. So you could take these lower half shift bits and shift them up to the upper 16 bits, and kind of save them off that way, and then reuse the lower half to bring another number in. Different things like that that you can mess around. There's all kinds of crazy things you can do with these registers, and that you end up having to do if you want to write super efficient programs that take advantage of all the register capabilities and avoid doing and minimize the number of swaps back and forth out to main memory, because going out to main memory is hundreds, thousands of times slower than just working directly with registers. So when you can keep the numbers you're working with or the data, it's not always numbers, sometimes it's text, but whatever data, whatever interpretation you're putting on these binary digits, whatever data you're working with, if you can keep it in registers and not have to copy anything from or to memory, your program is going to work much, much faster. And that, in fact, is the reason why there are still professional assembly language programmers when there is a need to write software that is as blindingly fast as it can possibly be. You want to take advantage of every trick in the book of assembly language program to write those things as fast as possible. Currently, compilers like a C compiler are pretty good at optimizing. So there's a lot of sort of built-in intelligence in modern compilers to try to take the human-written code and produce reasonably efficient machine language code. But most, like the standard GCC compiler that we're using is not producing optimized code. It's, if you are assigning things to variables there and doing calculations, it's moving stuff in and out of main memory all the time. And there's ways that we'll actually have a project where we look at it, look at taking what is produced by a C compiler and then making it much more efficient by editing the assembly language. Okay, so that's something to look forward to, but that's not for a few weeks yet. The main thing, though, I wanted you to just get clear in your mind what's going on with these half registers, and then the same thing applies to the half, the HX and LX, which are each half 1 byte out of AX. So just like these 8 bits that are all zeros right now, that's LX. And if you move just 1 byte into that, you're changing those bits out of EAX and so forth. So, but I just want to make sure that I actually pointed out the visualization of these two steps and exactly what was going on when we copied this FF00 into register AX. Again, if we switch this to look at hexadecimal, you see the FF00 right there. Remember, previously it was 5678. Now it's FF00 because we copied FF00 to those 2 bytes. All right. And again, whether it's 4 bytes or 2 bytes, it's always little endian. So again, if we look at the actual memory and we find this instruction, actually, if we click a little plus sign, we can find the address of that instruction. So that's 80480AF. So 80A0, 80A8, 80. So AF starts here at X66, XB8. So this is a 2-byte opcode, all right, not a 1-byte opcode. So the hex66, hex B8 is the opcode, and then the operand of 00FF, well, that's little endian, so again, that 00FF gets turned around to FF00. If we actually, let's see, this byte here is continue plus 9. If we want to look at that in words, let's see, this starts at, well, we have it right here. So let's actually just put this address in to our memory here. Go 0x8048OAF. So now our first byte here is the first byte of this instruction, and we see the 2-byte opcode, and then the 2-byte operand. And here again, it's little endian. So even though the number, the one word, the 2-byte number is FF00, in little endian it's 00FF. So whether it's a 2-byte word or a 1-byte or a 4-byte word or even an 8-byte word, a little endian means that the byte order gets reversed. Hopefully that's sinking in what little endian means now. Little endian talks about the byte order in memory and the byte order in a file on disk, if it's binary data. But little endian does not, the registers themselves are not little endian. And when you copy data from memory to the registers and from the registers to memory, the reversing of the order of the bytes is done for you, okay? So you don't have to think, oh, I'm copying 4 bytes from memory into the registers. Now I have to worry about them being in reverse order. No, the register, that copying process takes care of the reversal of the byte order, okay? So hopefully my constant talking about little endian every time it comes up is making that sink in a little bit. But the main thing about this video, once again, is, okay, 32-bit operation, 16-bit operation, and the half registers like AX, BX, CX, and DX are literally the lower half of the EAX, EBX, ECX, EDX registers. And so we actually saw that by copying this, and so it just basically replaced the 5, 6, 7, 8, but that 1, 2, 3, 4 is still there, which is what we can see. So there's the 1, 2, 3, 4, and we had 5, 6, 7, 8. We replaced that 5, 6, 7, 8 here with FF00 there. All right. So, yep, that's it for this video. Nice and short. But hopefully, if you had any doubts about that, it is now cleared up.